All right, so let's talk about 7.4. I included these notes in today's module, so you can print them off and write on them, or if you have like a tablet or something that you can write on, then you could just take notes directly on the page. But there's just a lot of definitions here and a lot of applications, as the title very well implies. So I figured it would be better to just have everything written out. So we're going to talk about vectors. Vectors are quantities that have both a magnitude and direction, as you probably know if you ever saw the movie Despicable Me. So they're different from other quantities that we're familiar with. Those are called scalars. And they are called scalars because scalars can scale vectors. They can make them bigger or smaller, but they won't change their direction, right? So a quantity that has both magnitude and direction is a vector. If it only has a magnitude assigned to it, then it's called a scalar. So for example, like velocity is a vector. So you can talk about like what speed you're traveling at, that would just be a scalar. But then when you assign a direction to that speed, now you've got velocity, and now you've got a vector on your hands. Same thing goes for acceleration or force. There are lots of physics types of application problems in this section, and I'll be honest with you, I'm not going to assign those problems because I think the appropriate place to talk about those kinds of problems is in a physics class. But we will talk about a couple application problems just so that you get the idea behind what vectors are and why we're interested in looking at them. In this section, we're just going to talk about vectors geometrically, and then in 7.5, we'll talk about vectors from a more algebraic perspective. So geometrically, vectors are represented as directed line segments. The length of that segment represents the vector's magnitude. The direction of the segment, the direction that the segment points represents the vector's direction, obviously. So here's an example of a couple vectors. This is vector OP, right? We start with the initial point O and then end with the terminal point P. This would be vector PO then, right? And so we can call vectors either by some name that we give them. So in this case, we might call this one vector U and this one vector A. Or we might describe them by their endpoints. So we call this one OP and this one PO. When we're writing down vectors in print, we either use bold-faced or we use an arrow over the top of the vector. I've used arrows over the top of all the vectors in this document because that's how you're going to write it down, since you don't really have a way to do bold-faced when you're writing things down by hand. So just so that you get used to seeing the notation this way. What else do we need to say here? The magnitude of a vector is denoted with absolute value bars around the vector, or sometimes some textbooks use a double absolute value. So like they might use a double OP to represent the magnitude of the vector instead of just a single absolute value. I don't know. I kind of like the absolute value notation myself, just the single absolute value notation, because if you think about what the absolute value does, it takes a real number that's negative, makes it positive. It takes a real number that's positive and keeps it positive. So it spits out the magnitude, right? That's what the absolute value is just the magnitude of a one-dimensional vector. We'll probably talk about that a little bit more in the next section. But anyway, some useful things about vectors. Or some pertinent facts anyway that'll help us through the problems in this section. So first of all, two vectors are equal if and only if they have the same direction and magnitude. And by the same direction, that means, first of all, the vectors have to be parallel. But second of all, they have to be pointing the same way. So kind of like we saw on the previous page, OP and PO did not represent the same vector. Okay, even though they were parallel, they weren't pointing the same way. So they have to be parallel, but they also have to be pointing in the same direction, and they have to be the same length, right? They have to have the same magnitude in order to be considered equal. The product of a scalar k and a vector u is a vector with magnitude, absolute value of k, times magnitude of u, that has the same direction as u, or possibly the opposite direction if k is a negative number. So in other words, if this first vector here is vector u, then this second vector here would be 2 times u. And you can see that it's pointing in the same direction as u, but it's twice the length, right? So this is 2u. This would be 3/2 u, so it's 1.5 times the length of our original vector, still pointing in the same direction. This is half u, right? It's half the length of our original vector, again, pointing in the same direction. And this one right here would be -2u. All right, so it's, first of all, it's twice the length of our original vector. But second of all, it's pointing in exactly the opposite direction of the original vector. So it's -2u. So that's how multiplication works between a scalar and a vector. If you're wondering, how does multiplication work between a vector and a vector? Well, there are different versions of multiplication, one of which we will be covering in the next section, called the dot product. So the dot product is a kind of multiplication that you can do with vectors, but it's not multiplication in the sense that you might be thinking. We'll talk about that again. We'll talk about that in the next section. But yeah, typically we don't talk about multiplying vectors. We can talk about their dot product, and that's about it. Which we'll and again we'll talk about that in the next section. Okay, so you can multiply a scalar and a vector. You can't really multiply. You can't really multiply a vector and a vector, but you can add a vector and a vector, right? So the sum of 2 vectors is also a vector, and it's called the resultant. There are a couple of ways to add vectors geometrically. Probably the most intuitive way to do it is to just place the vectors end to end, right? So if you're trying to add vector A plus vector B, then you would place vector A on the page, and then place the initial point of vector B on the terminal point of vector A. A plus B is it's this new vector that's formed by the initial point of A and the terminal point of B, right? So that would be vector A plus B. Another way to do the same thing is to use what's called the parallelogram rule. You'll have a couple homework problems that ask you, they'll say something like, use the parallelogram rule to do this or that. This is what they're referring to. The parallelogram rule, so to add 2 vectors using the parallelogram rule, what we do is we place the 2 vectors so that they start at the same place, right? So we put their initial points together. Now you can see that this is still vector A, right? It's still the same vector. And vector B is still the same vector. It's just that we've moved vector B from the end of A and moved it to the beginning of A, to the initial point of A, right? And that's a property of vectors. They're kind of independent of location. You can pick them up and move them around wherever you want, as long as you're not changing their magnitude or their direction. So, you know, we pick this thing up, move it over here to the other side. Now, the way that we get A plus B is we use these 2 sides to form a parallelogram, and then the diagonal of that parallelogram is the resultant. Okay, so that's 2 ways that you can add vectors. Both of those things will kind of come in handy as we look at some application problems here in a second. And then last but not least, you know, we can subtract 2 vectors by just adding the opposite. So u minus v is just u plus negative v, right? So you flip v around. If v is pointing, say, this way, then you flip v around, and then you just add u plus negative v. And that's all there is to that. I guess I should mention, you know, we've talked about multiplying 2 vectors. We've talked about multiplying a scalar and a vector. We've talked about adding 2 vectors. I suppose we should talk about adding a scalar and a vector. That's easy enough. It can't be done. It's nonsense, right? So you can't add a scalar to a vector. Okay. Now, because of the parallelogram rule, because we sometimes add vectors this way, it might come in handy to have a couple of facts about parallelograms. So first of all, opposite sides and opposite angles of a parallelogram are equal, and adjacent angles are supplementary. So if we're looking at this parallelogram, right, this side and this side are the same, this side and this side are the same, but also opposite angles are the same. So this angle and this angle are equal. This angle and this angle are equal. And adjacent side angles, so this angle plus this angle is supplementary. So this angle plus this angle is 180, right? And the same thing for every other pair. 180 here, 180 here, and 180 there. All of those facts just follow from what we know about transversals, since these are parallel sides and this is a transversal cutting across them. Anyway, another fact is that the diagonals of a parallelogram bisect each other. So if we were to draw in the other diagonal, where they intersect bisects both the diagonals. So these two lengths are the same, and these two lengths are the same, right? So I don't know. I'm not sure if those will come in handy. They might. So we'll keep those in mind as we look at a couple examples. So I want to go through 3 examples with you. I think they're like the book goes through like 6 examples. You're welcome to read through the other ones that I'm not going to cover here. Sorry, you're welcome to look through the other ones that I'm not covering here. I just like I said, I'm going to skip some of the more physics-y types of problems because I think, like I said, the appropriate place for those is in a physics class. But let's look at this one. So it says 2 forces of 15 and 22 newtons act on a point in the plane. If the angle between the forces is 100 degrees, I don't know why that circles down so low. I probably made some kind of mistake when I was typing this up. Anyway, but if the angle between the forces is 100 degrees, find the magnitude of the resultant force. Okay, so we have 2 forces, 15 and 22 newtons. I'm going to start to draw a picture here. So I'm going to say that this is my 15 Newton force. And then I have another 22 Newton force acting on this same point. We could give that point a name. I don't know if it's really important. Maybe I'll call it point A. So we have another force, 22 newtons. And the angle between this first force and this other force is 100 degrees. So 90 degrees would be, straight up. 100 degrees would be a little bit more than that. And it's 22 newtons, so I'm going to draw it a little bit longer than I drew the first force, right? So there's 22 newtons. And we want to find the magnitude of the resultant. Maybe I can label this as 100 degrees. We want to find the magnitude of the resultant force. Okay, so what I'll do is I'll probably use the parallelogram version of this. So I'm just gonna sort of complete the parallelogram. And I know because of the rules that we just talked about, that wasn't very good. I know because of the rules we just talked about that this angle right here is 100 degrees. Not sure if that'll come in handy particularly, but I also know that this angle and this angle are supplementary, so that should be 80 degrees right there and 80 degrees right there. Again, not sure if that'll come in handy, but now I also know that this is 22 newtons because opposite sides are equal. So that's 22 newtons and that's 15 newtons. Anyway, what is it that I'm trying to find? Well, I'm trying to find the diagonal of this parallelogram. Well, specifically, I'm trying to find the length of that diagonal, right? Because I want to find the magnitude of the resultant force. Well, I've got a little triangle here. Maybe if I labeled these points, it would be a little easier. So if I call this point B and I call this point C. Now I've got triangle ABC here, and I know side, angle, side information. So, and then what I need to know is the opposite side. So I'm thinking like law of sines might come in handy here. I could say something like sine 80 degrees over this diagonal. Well, I need another angle, don't I? And I don't have another angle. Well, so maybe not law of sines. Maybe law of cosines then. So I can use the law of cos. Yeah, law of cosines would be better, right? I can use the law of cosines that uses angle C to solve for side C's. That's what I'm going to do. Okay, so law of cosines that involves angle C is this one. C squared equals A squared plus B squared minus 2AB cosine C. In other words, C squared is A squared plus B squared minus 2 times A times B times cosine of C. I'm just going to punch all that into my calculator. Actually, I'll take the square root as I go. So I'm just going to go ahead and take the square root of this nasty thing. So we'll have square root of 22 squared plus 15 squared minus 2 times 22 times 15 times cosine of 80. Make sure you're in degree mode. Okay. Yep, that's all in there correctly. That looks pretty good. And so it comes out to, well, how many sig figs? I guess 2 significant figures. So we'll say 24, about 24 newtons, right? So that would be the magnitude of that side. So you can see that this is really nothing new. It's just we're using new words to describe the scenario, right? The resultant, fancy schmancy word. Anyway, but yeah, 24 newtons. I guess, you know, if we were being a stickler for notation, we could say, well, if this is vector v, then the magnitude of vector v is 24 newtons, right? But anyway, but that's the idea there. Let's look at another one. So this was a new word for me, I'll be honest with you. The equilibrant, I guess is how you say it. I don't know. I didn't bother to look it up before I started recording this video, but I'm going to call it the equilibrant. The equilibrant of a vector is a vector that counterbalances the resultant. So if you've got a couple forces or whatever, and you find the resultant force, then the equilibrant is just the opposite of that, right? So it counterbalances the resultant. Anyway, this one says find the magnitude of the equilibrant of forces 48 newtons and 60 newtons acting on a point if the angle between the forces is 50 degrees. Then find the angle between the equilibrant and the 48 Newton force. Well, okay. So let's start off by drawing a picture. So we have two forces, a 48 Newton force and a 60 Newton force acting on some point. So I'm going to start off drawing pretty much the same picture that I drew before. So we've got a 48 Newton force there, and then a 60 Newton force. This time the angle between them is only 50 degrees. So maybe something like that. But it's 60, 60 newtons. I'm going to draw it a little bit longer. Okay, so that's my dog in the background. If you couldn't tell, that was a dog. The mailman is here. Mail carrier, I should say. It's a woman. And for some reason, the mailman is my dog's worst enemy. She won't bark at anything else, just the, just the mailman. Anyway, okay. So I don't know how well I'm drawing this to scale or anything like that. I'm pretty certain it's probably not to scale, but that's all right. So so again, I want to find the equilibrant, or the did I say that right? Equilibrant. Yeah, I want to find the equilibrant. In order to do that, the equilibrant is just the opposite of the resultant. So if I start off by finding the resultant, then I've got the equilibrant in the bag. So I'm gonna do the same thing, use the parallelogram version of addition. So right away I can label this 60 newtons, 48 newtons. And I'm trying to find the resultant, which is this vector right here. And I know that these angles right here are supplementary. So if this angle is 50 degrees, then this angle right here should be, well, 130 degrees, right? 180 degrees minus 50 degrees would be 130 degrees. And so now I've got a very similar situation to what I had before, right? In example 1, I've got a side angle side. So so I can find this magnitude pretty easily. And of course, the magnitude of this vector is going to be the same as the magnitude of, so this is the resultant, right? The magnitude of the resultant is going to be the same as the magnitude of the equilibrant. The equilibrant, I guess we might as well draw it in, would just be the same vector pointing in the opposite direction, right? Same length, complete, like exact opposite direction, if that makes sense. So this is really the vector that we're interested in, but it has the same magnitude as this guy here. So again, I'm going to use law of cosines. So let me label some stuff again. Again, I'll call this point A, point B, and point C. And I'm going to use the same version of law of cosines here to solve for the magnitude. I'm going to say c squared equals a squared plus b squared minus 2ab cosine c. Okay, so I'll let you work. Maybe I'll give this a name, equilibrant. So maybe I'll call it E for equilibrant. And so instead of c squared, I'm going to say magnitude of E is really the same thing as c, which is approximately square root of 60 squared plus 48 squared minus 2 times 60 times 48 times cosine 130. That's about 98. How many sig figs did we get? Still 2, so we'll say it's approximately 98 newtons. Okay? That kind of checks out visually. I mean, it does look quite a bit longer than the other two, so I suppose that makes some sense. But we're not done, right? We wanted to find, it said to find the magnitude of the equilibrant, but then it also said to find the angle between the equilibrant and the 48 Newton force. So in other words, we want to find this angle right here. Okay. Well, how are we going to do this? I mean, I suppose, you know, obviously this is just a straight angle right here, 180 degrees. So if we knew what this little angle was, then we can say, well, this is 180 degrees minus whatever that is. So how do we get that angle? I mean, I suppose we should just use a law of sines or something, or law of cosines, right? We could use law of cosines or law of sines. I'm going to use law of sines. I think law of sines is a little easier. So I want to find this angle right here. And I know it's opposite side, right? So law of sines will work. I'm going to say, since I know that this is about 98, I'm going to say sine C. Uh-oh, my family just got home. Someone's going to burst in, I'm sure. Anyway, sine 130 over 98. So that's sine C over C, right? Sine 130 over 98 equals, we'll say sine, oh, what should we call this? Alpha, maybe? We'll say it's sine alpha over 60. And then we can solve for alpha. So, so sine alpha is 60 sine 130 over 98. So alpha is sine inverse of 60 sine 130 over 98. Let's see about how much that is. So sine inverse of 60 sine 130 over 98 is about, well, again, to 2 sig figs, this would be about 28 degrees. That means the angle that we're looking for is going to be 180 minus 28. So maybe instead of calling this a question mark, maybe I'll call it something else. But maybe I'll call it like beta or something like that. We'll say beta is 180 minus 28. So 152. So it would be about 152 degrees, right? So there's the magnitude of the vector, and there's the angle that it makes with the 48 Newton force. Okay, as you can see, being able to draw a picture is of paramount importance to being able to solve these kinds of problems, right? So, and if you're staring at the problem thinking, I have no idea where to begin, start by drawing a picture. It will help you. I mean, I haven't looked at these problems prior to working them out, you know what I mean? So I'm just kind of letting the picture guide me. But that's that idea. Let's look at, I just want to give you one more. This will relate all of this stuff back to stuff that we've done in the past, right? So this one says a ship leaves port on a bearing of 28 degrees. And remember, when it doesn't give you the bearing like, you know, 28, like north 28 degrees south or whatever, or north 28 degrees east, it's assumed that this is 28 degrees from the north, okay? Anyway, so it leaves on a bearing of 28 degrees and travels 8.2 miles. The ship then turns due east and travels for 4.3 miles. How far is the ship from port? And what is its bearing from port? Okay, so it leaves port. I'm going to say the port is down here. Maybe I'll call it P for port. And it leaves on a bearing of 28 degrees. So that's 28 degrees measured from the north, right? So 28 degrees from due north. So it's going off kind of in this sort of direction. And it does that for a while, right? Does that for 8.2 miles. And then it turns due east. So it goes due east for how far? 4.3 miles, so about half as long. So 4.3 miles. And then we want to know how far the ship is from port. Right, so remember, this is port, this is the ending place. So we want to know what is this distance here. And what's the bearing? So we want to know what's its bearing from port. In other words, like, what is its angle from the north? So we want to know that angle, which means most likely we're going to be finding this little angle so that we can add these two things together here in a second. Okay. So what are we going to do about this thing? So I need to know this angle here. Maybe, okay, so maybe what I'll do is notice that if I draw another vertical line through that point, now the 28 degrees here and this angle here are alternate interior angles, and that means they're the same. So that's 28 degrees. Meanwhile, the ship went due east, so you know that from the south, this is a 90-degree angle. So, consequently, I can conclude that this angle here is 28 degrees plus 90 degrees. So that should be 118 degrees. There might be another way to figure that out that's maybe a little bit easier. I don't know. But that's how I figured it out. As long as you get there, I guess it's fine, you know? Well, anyway, now at this point, this is just exactly the same as the other two problems, right? We've got, hey, look at that, side angle, side. I'm going to use, oh, you guessed it, law of cosines to find this magnitude down here, right? Maybe I'll label this point something else. So that's port, and this is its ending location. So maybe I'll call it like L or something. L for location. Anyway, so so we can say so I'm going to say magnitude of PL squared, right? So that length squared, so this is C squared equals A squared plus B squared minus 2AB cosine C, cosine 118. So I'm going to go ahead and take the square root of all of that as I punch it into my calculator. So we've got square root of 8.2 squared plus 4.3 squared minus 2 times 8.2 times 4.3 times cosine 118. Oh, yeah, 10 point. So to 3, I think we had 3 sig figs starting out. So to 3 sig figs, we would say this is approximately 10.9 miles. So that's how far the ship is from port. What's its bearing from port? What's its bearing from port? In other words, we want to know what's this angle from the north. Right? We want to know what that angle is right there. In order to get it, we should first probably figure out what this angle is. If we can figure out this angle, then we can just add it to 28 to find this big angle. Unless there's an easier way. Is there an easier way to do this? Maybe. Well, no. I don't know. I don't know if there's an easier way to do it. I'm just gonna, maybe there is. Maybe you can sit there and scratch your head and figure out an easier way to just figure that out. I'm just gonna use probably law of sines to find this angle, and then I can add them up to find the bearing. So employing law of sines, right, I know this side now is about 10.9. So I can say sine 118 over 10.9 equals sine p over 4.3. I'm just calling this little angle p, I guess. It's sort of ambiguous which one I'm talking about, but anyway, so then sine p is going to be 4.3 sine 118 over 10.9, which means p is going to be sine inverse of that junk. So sine inverse, 4.3 times sine 118 over 10.9 is about, to 3 sig figs, it's about 20.4 degrees. So this is about 20.4 degrees now. So then the bearing, right, the bearing of the ship would be 28.0 plus 20.4 degrees, 48.4 degrees from the north. And that'll do it for this section.